Hello, everyone. Welcome to week 3, SIGPwny. Today, we're gonna revisit kind of our third iteration of Cohen's, talking about return-oriented programming, or ROP. So the nice announcements, we have Tracerfire coming up. It is a security cyber defense competition ran by Sandia National Laboratories. There'll be food and prizes. Sign up. There's a link on Discord. There's a link on this presentation. There's spots limited and registration closes on the 15th. Come to SAIL. If you want to present at SAIL, it's a opportunity to teach incoming high schoolers about CS and other topics. There's an application, apply by the 17th. Again, there will be food, free t-shirt, so on. This Friday, tomorrow, we are competing in LACTF, one big team. We will find a room, commandeer one somewhere in Siebel, and we will bring in pizza, and it will be a good time. Ideally, we can get friends. Yes.
What does the LA stand?
Out Los Angeles. I believe it's the CTF run by UCLA. So it's their kind of big CTF. All right. Cool. So that's our meeting flag for today. If you go to ctf.sigpwny.com and look for the category of Home 3, there will be a meeting flag. Type that in. It's 5 rets separated by underscores. We'll give you a few minutes to do that.
I think they told us what it was.
I can do it from here. Okay. This will be available on the SIGPwny Discord later. So, since it's been a bit since we've talked about Pwn, I want to do a bit of a review, especially if you haven't been with us last semester or kind of forgot. So Pwn is the idea of gaining control of a binary so that you can, pop a shell, get access to the entire system that's running the program, and reroute code execution to do something that you want to do rather than the intended way. So we have a really basic C program here that declares a buffer of 32 bytes and then runs gets. Gets is traditionally the very unsafe read in a string from standard in. It provides no length checking, so it's very easy to overflow the buffer and smash the stack. So on the stack, we have our local variable for the buffer, which takes up 32 bytes, the saved base pointer, and then the saved return address of where this function returns back to when it finishes execution. If we just spam it with, say, A's, we replace all of those values with an A, and the program, without any tweaking or fine tuning about it, will crash. So we have kind of 2 introductory ways to do Pwn. The first method that is kind of colloquially called ret to win is there's a win function in the binary. It's at some address in the code. You change the return address to be that win function, and presumably it prints out a flag. The other way to do it is called ret to shell code. You write some shell code, which is assembly that just runs execve to pop a shell, get access to the main system, and you return back to the stack and run the shell code that's on the stack. And there's some basic mitigations that we can do to prevent these types of Pwn. The first mitigation is called a stack canary. We'll place some random bytes before the return pointer on the stack, and before we return, we check that those random bytes have stayed the same. If they haven't, we crash and cancel the program. The other form of basic mitigation that we have is setting the stack, the memory region involved that holds all that data, as non-executable. This prevents ret to shell code, as you can't write code in your stack anymore to execute. And so places within your program like the stack or the heap is read write, whereas the code in the text segment is read and execute. The basic philosophy that security, like programmers and security engineers have adopted, is that any region of memory in your binary is either write, X, or execute. So never both, but you can't have one. You never want the user to be able to write the code of the program while it's running. So how do we bypass this? Well, about almost 2 decades ago, a paper came out introducing return-oriented programming. The idea is that we execute tiny bits of code, which we'll refer to as gadgets, to achieve the same effect as shell code. These already exist in the binary, and instead of it being input that the user has put in to try and be malicious about it. This completely bypasses non-executable stack because we're jumping between bits of code in the executable region of the binary. So our goal is to find and return to these gadgets and organize them into a meaningful program. So at a high level, say we want to achieve setting the variable b to b3, and we have these 4 tiny gadgets here of a equals a plus 1, a equals 0, b equals a, and c equals b. Can anyone tell me, and you can use these gadgets as many times as you want, can anyone tell me how to arrange these gadgets into a program that achieves b equals 3? Yes.
A equals 0, a equals a plus 1, a equals a plus 1, a equals a plus 1, b equals a.
Exactly. We just string those gadgets together and we achieve our b equals 3. And so that's the very high level of what ROP is trying to do. Now we have x86 assembly. This is almost exactly the same. There are hints on the side of what each of these gadgets kind of do. Our variables are now register names, RAX, RBX, so on. And we have these little return statements, which we're not going to worry about right at the moment. So again, achieve the same thing, set RBX equal to 3.
What does the NFP?
No op, so nothing happens.
What does Rax and RBX start with?
You don't know. So gadget 2 will set RBX to 0, because if you XOR a 64-bit integer with itself, you zero out all of the bits. So that may be one way to get that register to 0.
Also, you could use gadget 2 and set RBX to 0. Actually, sorry, you could use gadget 3 and set RCX to 0.
Yeah. Mhm. Yeah. So if you didn't hear that, we first set RBX to 0, so we now have a number that we know that we're working with. We swap RAX and RBX, so now RAX is 0. We increment RAX 3 times, and then we swap them back to get RBX equal to 3. So that effectively is what ROP is trying to do. We have these gadgets of assembly, which are terminated by these little ret statements, and we're trying to organize them into a meaningful program. So our strategy then is to find gadgets in our program that set up the exec.ve syscall, which is what it allows us to run a secondary program, ideally a shell. And we need a gadget to call syscall itself, which will actually call the function. So we'll order these gadgets into a program that sets up the registers and calls exec.ve/bin/sh, or some similar shell popping program. Sometimes system exists if you have like libc available, and then we're going to execute it by setting the original return statement to our first gadget. So how do we find gadgets in the first place? Any C code will be translated into assembly. And the one important thing to always remember is that code is just data. So somewhere in our binary, this function will be stored at some address. But later assembly commands will be stored at later addresses. It's a variable length, it's x86. But at some point, let's say, for example, at hex value 406032, this pop RBP is before this ret. So instead of returning to a function, we just return to the middle of a function, right before a return statement. And so any bit of code followed by a return statement is a gadget. And we can use this command on Linux that dumps all the objects and kind of filters out the like last 5 lines before a return statement. Pwn tools, when you start making exploits, also has a tool to help you find and locate gadgets and deal with them in a symbolic way. That library is rop.rop. So what does ROP execution look like? When we have our gadgets found and what we want to do and actually like making a meaningful program, we overflow our buffer, set the return address to our first gadget, and then set the next 8 bytes to the second address of the return gadget of the second address of our next gadget, and so on. And we do this for as many gadgets as we have. Why does this work? Well, if we don't really mess with that stack that much, what happens is every time we call return in an assembly, it will move the base pointer, I think. It'll move the base pointer and change where the return address is by 8 bytes every time we call ret. So if we avoid the whole like setting up the stack and allocating stack that's present in almost every function when it has its own local variables, what will happen is we'll run a bit of code, return the pointer pointing to the return address decrements or increments by 8 bytes, and then it'll just return again. It'll keep doing that without actually ever going back to the original function, because we never set up a new return address properly. So what does how do you perform ROP yourself? Well, you can do it manually using that object dump and setting up a ROP chain yourself. If you take 461, that's what you're going to have to do. But there are easier methods because this is a very common thing to happen now. There's 2 tools that I really recommend. One is ROP gadget, which will allow you to list out your gadgets that is in a binary or a library, or just create a ROP chain itself to pop a shell. It'll just give you the series of return addresses that you need. Or somewhat more in a fancy way, there's a tool called OneGadget, which if there is exactly one place to return to that will pop a shell, it will show you where to return to, but what registers need to be set, and that will achieve the same results. So I want to talk about some ROP mitigations that people have implemented and kind of came around before and after at the same time. There's PI, which is position independent executable. This allows a binary to have any address as a space address of where the code is stored. So if you opened up a binary in your decompiler, it will have the code at some address, and if PI is disabled, you can use that address during execution. If PI is enabled, it might be that that address is randomized and that you will have to get a leak to where the code is to know where to return to in functions. And then there's also ASLR, which is address space layout randomization. So on top of the text segment, which contains your code, both the heap and the stack and anything else can have random base addresses, which makes things way more complicated. And then you need a leak for any memory region you want to mess with, which can be hard to get. Yes.
Does that like dramatically slow down your execution?
Surprisingly not, because we all use relative addressing. So instead of like having hard-coded values, you're doing the relative. So there's a bit of slowdown, but security has always been about finding that fine line of safe versus performant. Of course, if you want the most performant program, you drop all security mitigations and then you're running free. But then you're vulnerable to almost everything that's out there. I don't believe ASLR is that much of a slowdown for what you gain from it from a end user point of view. All right. So if both are disabled when you're doing an exploit, you can open the program with GDB and run info file, and I will tell you where all the memory regions are located, and you can use between exploits. So then let's talk about libc. So your program most likely will be less than 15 kilobytes, which is not enough for any meaningful ROP chain to allow you to pop a shell. Luckily, almost every C program dynamically links the libc, which has all of your favorite functions like printf, gets, wrappers to syscalls, all that good stuff. Anytime you use an include statement from standard library, that's libc. So we're instead gonna probably look for gadgets in libc. So we can, instead of using a binary, we can just pass the library file into one gadget or Pro Tools or object dump. It'll take longer because those files are larger. During execution, we're going to probably need to leak a libc address to see where that code is located in our virtual memory space. Because it's dynamically linked, it's not something that you can always know where the base address is. Also dependent on like if ASLR is on Pi and whatnot. Once you have that libc address, you can calculate the libc base from that leak. So where does libc start? There's a database that allows you to figure out which version of libc you're using and where each of the functions are located relative to each other, which is how you can do this offset calculation by hand. Once you do that, you can add your gadget offset to each of your addresses that you know of, and do execute your ROP chain. So I have a Pwn Tools example script. This kind of introduces a few other techniques that you may have not been aware of with Pwn Tools. So the very nice thing that Pwn Tools has is ELF, which loads a giant symbolic like object of the binary or library that you've loaded. So this allows you to keep track of where the base address of your binary is when you find it, and you can use ROP.findGadget and use the symbols to help automate this process and make you want to pull out your hair a lot less. So there's a lot of really neat tricks you can do with this. If you have any questions about how to use Pwn Tools to this extent, feel free to ask. I do want to talk a bit about modern ROP mitigations, because since that paper has come out, a lot of exploits still use ROP to this day. But people have been getting a bit better on how to deal with, hijacking control flow. So one of the methods is signed return pointers or pointer authentication. So it checks to make sure that the pointer was signed by the program and being used by the program, and that the return address is a valid location to return to. So instead of necessarily in the middle of functions, it's always after a call or at the start of a function. And then there's branch tracing and abnormal execution. Usually your CPU has some efficiency speed ups for jumping to very local places, but it is slow when it needs to jump to different functions. So some security mitigations have learned to track how the CPU is jumping between function calls to help mitigate and crash quickly if it notices it's jumping wildly everywhere, like ROP wants to do. So on the side, I have a bunch of resources that you can go find all these tools. I have Pwn Debug, which is, if you don't have it installed for GDB, I highly recommend it. It makes your life a lot easier when debugging your program. Pwn Tools, ROP-Gadget, OneGadget, the libc database search. There's some additional practice and constraint solve ROP chain resources with ROP Emporium and Anger ROP. And if you haven't seen the previous Pwn meetings or a bit confused on x86 assembly, I've linked to the old meetings on the sites as well. So next meetings, again, tomorrow, LACTF, be there. We will make an announcement in SIGPwny. And this Sunday, Kevin will be talking about heap pwn, which is being able to leak addresses and other artifacts from allocating memory on the heap and getting arbitrary execution from that. All right, that's that. There's a few challenges from last year that are on the website, so feel free to try them out. Raise your hand if you have any questions. And yeah,